Good morning, guys. So welcome back. Today we're going to finish our last section of this particular unit involving solving nonlinear systems of equations. It doesn't sounds bad, but it's really not. It's just going to be the same things you've always been doing. It's going to be just elimination and substitution, just not with things are lines. There's going to be like x squared things. The analysis will be the same as always, so I don't think it'll take much explanation, and it'll be an easy day for you. All right, so let's solve these following quadratic inequalities. So write down number 1. It says that 0 is less than or equal to x squared plus y. So most things you would want to get y by itself. This is no different. So you're not trying to graph it or get a feel for it. You want to get y by itself. So if I was going to do that, I'd probably just subtract the x squared over. And then I'd say that y is greater than, can you read it backwards? Y is greater than or equal to negative x squared. Now, what's a graph of negative x squared look like? Well, x squared opens up, correct? So what's the negative in front of something do? Anybody remember? Yeah, it flips it down. So this graph, and I'm going to draw it nice and solid, looks something like this-ish right here. Quadratic opening down. And if you can read it backwards, that's great. If you can't, write it in the other order. Remember, it always opens towards a bigger one, right? So y is greater than or equal to negative x squared. So we want to shade this thing above it. Any y's above it. And remember, when you have y's and x's, those are the problems that are going to have shading involved. This one had shading. We shaved above it, and we are good. So that's all there is to number 1 on this particular problem. Shade above it, get the y by itself, and that's it. So there's the answer for number 1. Number 2, let's see about this thing. So in number 2 today, I see y's again. So I'm going to be trying to shade things. I'm going to draw this very carefully. So let's see what we can do with this thing. Well, if you're trying to just draw an accurate graph of it, you might want to know where the vertex is. And this good old equation, x is negative b over 2a, that's a good equation to figure out where the vertex is. B is negative 2, so negative 2 would be positive 2 on top. And on bottom, 2 times a is 1, would be 2. So we know this vertex is going to be at x equals 1. So I want to go over here to 1. And I know somewhere on this line, this axis of symmetry will be my vertex. Don't forget, if you ever need to find the y coordinate of something, you know the x, all you got to do is plug it in. You plug 1 in here, 1 squared is 1. 2 times 1 is 2. So 1 minus 2 is negative 1. And negative 1 minus 3 is negative 4. So right down there at negative 4, that's where my vertex is going to be. This quadratic is going to open upwards. So I'm just trying to get a rough sketch of this thing. It doesn't have to be perfect, but the vertex is at least one thing I want to focus on. And I should just made a mistake. What should I have done differently when I drew that? Should have been dash, right? Yeah, if it's less than, remember it's not less than or equal to, so I can just erase some things, easy fix, no big deal, a little dash line here. Dash, dash, dash. And this one, we're looking for y's that are less than this thing, so those are the ones that are below it. So just shade below that dash line. And we're good on that one. So it took a minute or so, but don't forget that x equals negative b over 2a. It's very useful to figure out what the center of this thing is going to be. All right, and then lastly, number 3, we have one that does not have y's. So there will not be shading. These kind of questions are the ones where there's going to be intervals. So it's going to be from here to there and there to there. But we got x squared plus 3x minus 1 greater than or equal to 0. For this one, for these kind of problems, since you're looking for when the graph itself is above the axis or below the axis, you really want to know where it crosses the axis. So I'd love to find these zeros right here. And lots of ways to find zeros. You can factor, you can complete the square. I don't think this factors. Anybody think this factors? I don't think it does either. So we could just probably default back to our quadratic formula to figure out where it crosses without much thought. So quadratic formula time, x equals negative b plus or minus the square root of b squared. B squared would be 9 minus 4ac. 4 times 1 times negative 1. And that's all over 2a, and a was 1, so 2 times 1 is 2. And then inside that discriminant, remember that means the stuff inside the square root, you got 2 negatives, so it's really going to be a positive. So it's really 9 plus 4, which is 13. So negative 3 plus or minus the square root of 13 over 2. You ask yourself, can you do better? And you look at your perfect squares, and no, 4 and 9, they don't go into 13. So nothing reduces. So these are the two clean answers we're going to get. One of them will be on one side, and the other one probably on the other side. This one's going to be -3 plus the square root of 13 over 2. The other one's -3 minus square root of 13 over 2. Doesn't really matter where you place them. The key one thing is that the plus one's going to be on the right, and the minus one's going to be on the left. And then once you get a clean graph of this thing, which opens upwards, correct? So it looks something like this. It doesn't really matter where you drew it on the axis. The key thing is, where is this graph above 0? Well, it's above 0 anywhere up until this point, correct? And then anywhere from this weird number on, it's also above 0. So putting this all together, -infinity until the first one, it would be above 0. Should I use a bracket or parentheses? I put a parentheses, is that right? No, it can equal 0. So you actually want to include these two numbers in your answer. So -infinity up until that weird number at first and including it, and then skipping over the stuff where it's below the axis. And then similarly, another bracket on the other one for the same exact reason. It does include it, it does equal it, and then all the way to infinity. So that's kind of how you're going to do those kind of problems. And hopefully your homework wasn't too bad about that. All right, let's do some learning goals and get you guys learning. Woo! Here we go. Learning goals today. Students will learn to solve systems of nonlinear equations. Students will learn to solve systems of nonlinear equations. That's the goal for the day. Internet's being very funny today. Of course, you got new homework. So your one from last week is due today. You have a new assignment, and that'll be right out of the book or online, whichever one you prefer. There it is. It's called 3.8 down at the bottom of the screen. Take a second to write that down. It's found on page 195. Numbers 1 through 9 all. And 25 through 65, but just multiples of 5. So 25, 30, 35, 40, 45, 50, etc. 55. 3.7 due today. There's 3.8. Due Monday after the break. So if you want to not have homework over the break, I would strongly suggest you use the work time today and tomorrow in class to get this taken care of. And that's your goal. Get that thing over with. All right. Let's go ahead and see what else we can do now. So notes. Today's topic, section 3.8, the last one. Here's the title of it if you like to write down titles. Solving linear, nonlinear systems. So basically any system of equations, anything. They could throw anything at you. But they're going to keep it to quadratics and lines. Nonetheless, the ideas from the past units still apply. Consistent and inconsistent kind of stuff. Dependent, independent kind of stuff. But just with more complicated things. So I really don't think there's much I need to say as far as theory goes. Let's just kind of look at some examples real quick down here. Write down this example. Example number 1. Solve the system of equations. So these are funkier looking things. It's got squares and y's and all kinds of things mixed up together. Nonetheless, all the same theory and strategies from previous units still apply. If you want to do substitution, get something by itself and substitute it into the other equation. If you want to use elimination, you can do that too. If you have the exact same kind of terms on the top in both equations, you may eliminate things as well. Still a very big proponent of substitution. So guys, I think, isn't x already solved for in equation 1? Well, same thing as always. If it's solved for in here, you just substitute it in here and clean it up a little bit. So plugging x in from equation 1 into equation 2, and be nice and careful. You know how these things go. If you mess up one little sign or something like that, it's all jacked up. It says -x. So negative, and then all of what x is. So make sure you put parentheses and stuff. Negative x was 2y squared plus 3y plus 1. So I'm rewriting equation 2. That's just the negative x part, negative x plus y equals -1. And just like before, now you're down to one equation with one unknown. And it's just going to take some distribution, some cleaning things up, and we'll see what we get. Distributing, I see -2y squared. I see -3y, but what else is on this side of the equation? There's a y, right? Oh, so altogether, that's -2y. So I got -3y from the distribution plus a y. And then I've got a -1. You see the -1? But look what's on the other side of the equation. Well, -1, right? So you can just add 1 to both sides while you're at it if you want. And it's just going to turn into this equation, -2y squared minus 2y equals 0. So with any quadratic, now it's down to how do I solve a quadratic? Well, the first thing you want to scan for is, before you even start factoring or quadratic formula or anything, is there anything that they all have in common? I think so. Yeah, I think negatives also, they both kind of negative, right? There's a negative, a 2, and a y. So let's factor out a negative, a 2, and a y. Factoring is good, always good, always good. When you do, that one's just y. And what's left from this? 1. Yes, a +1 is still hanging out there. All right. So the whole reason you try to factor is because then you can just look at when the factors themselves are equal to 0. And factors are just things multiplied together. I see this thing times that thing. It's like two separate things. Well, let's go figure out when they're 0. This one. When does -2y equal 0? Well, if you just divide by -2, what's 0 divided by anything? Still 0. So this answer says y equals 0. And the other one over here, y plus 1, if I set that equal to 0, then that implies y equals -1. Now, the only thing different from what you're used to with lines is that with lines, how many places could they cross? Basically, they could cross at maybe one spot, correct? These things are curvy things. You know, this is some kind of weird quadratic, and here's another thing. How many spots could they cross at? Maybe 2. So you might get out multiple answers this time. You got out 2 y's, right? Y could be 0 or y could be -1. But in either case, you do the same thing. If you got one of them, you go back and plug it in, right? So if y is 0, let's see. Let's plug it into this one. That looks nice. If y is 0, then that's 0, correct? That's 0, right? So x would be 1. So for this option, I'm getting the coordinate x is 1, y is 0. But I had another y option, so I need to test that and plug that back in too. So if you get 2 answers, you got to go back and get 2 different x's and stuff. Y is -1. If you plug it in somewhere right here, this one actually looks easier to me. If y is -1, this would be -1. This is a -1 too, right? So if you get them to go away, then -x equals 0, which means x is 0. So you back substitute and figure out the other one is. So this has 2 solutions. It has solutions, so since you're doing systems of equations, make sure you write your buzzwords. They have solutions, so you write consistent, right? And it's not an infinite number of answers. There's 2 answers, that one and that one. So consistent and our good friend that we usually write, independent. Consistent and independent. Same old stuff as always. Nothing new about it. Let's try, this one looks interesting. Let's try this one. Yeah. Example number 2. Let's try it out. This one, x squared equals y plus 5. And -x plus y is apparently equal to 7. All right, so you can do the same things as always. I would still recommend substitution, but you can do elimination. What do both these equations have that are exactly the same thing? This has a y and this has a y, right? So you could subtract them kind of and get the y's to be eliminated, and that'd be fine. Could you eliminate the x's on this one? The answer is no, right? These are squares, these are linear, so be careful about that. That's the one thing with elimination that might not always work out, is that they're not the same kind of terms. No matter what you do, it's not going to work out. Let's do elimination just to spice it up. Now, the only thing that's confusing to me is I have, in this equation, I have the y's on the right. In this equation, I have the y's on the left. So since I'm trying to eliminate my y's, maybe I'll get my y's on the same side. Doesn't matter how you do that. Let's take the first equation and move the y over. So equation 1, x squared minus y is 5. Second equation we're going to leave unchanged. And it's just good to have things lined up like this, looking the exact same thing. I got x's on the left and y's on the left and numbers on the right. We're good. So since we're trying to eliminate the y's, would I add or subtract these equations? Add or subtract? Add. Agreed. So I'm going to add these two things together. Now, these aren't like terms. Nonetheless, I can still add them. What's x squared plus negative x? Well, you can't put them together, so it's x squared plus negative x, or x squared minus x right there. The y's, of course, go away. And on the right side, 5 plus 7 is 12. So elimination is another option. Could have done substitution on this. You pick your poison. It doesn't matter. I'm just kind of showing you different options. Like any quadratic, you should think, oh, I need to go set this equal to 0. 0 is important. Because if it's not set equals 0, I can't factor. It's pointless. I can't use quadratic formula. It's pointless. Does this factor? I don't think it does. When I see 12, I'm thinking maybe 4 and 3s. And if one's positive and one's negative, that would work out. Negative 4 times positive 3 would be negative 12. Their sum is, in fact, negative 1 as desired. So if I factored it, great. That means that my two answers or whatever make these factors 0. What makes x minus 4 equal to 0? X being 4. What makes x plus 3 equal to 0? X being negative 3. And now we got our x's. So just like before, you got two different answers. That's okay. Take them, plug them back in somewhere. Probably this one looks a little easier to work with, I would think. Maybe, I don't know. So going back to this first version of equation 2 or something like that, if x is 4, this would be negative 4, right? And to get y by itself, I'd add 4 over. 7 plus 4 is 11 in that case. The other one, if x is negative 3, well, then this would be negative 3, which would just be positive 3, right? And if you subtract 3 from both sides to move it over, 7 minus 3 would be 4. So here's two different answers. One coordinate of 4, 11 is where these two things cross. Apparently, it also crosses at the coordinate negative 3, 4. There's the answer. So, of course, the word consistent. And there's not an infinite number. They're not the same thing. Same tricks as before. If you got like 0 equals 0 or 5 equals 9 or something weird, you'd stop and say, okay, is it consistent or dependent or something weird like that? But that's kind of all there is to it. All right. Now, write down this example because you might need to know what they want when they ask you to do this. This is kind of stupid, actually, but this one is different. If you read the directions on example 3, it says, use a system of equations to solve this. Doesn't look like a system of equations to me, and I would not recommend solving this with a system of equations. Kind of stupid. But if the book asks you to solve something that has just one equation with a system of equations, how do you go about doing that? You kind of go the other way. You make two equations out of this. So one of them you call the left side. The other equation you call the right side. This is very stupid. I would not do this. I mean, in practice, if I saw this, I would just move everything to one side and try to factor it. But for some reason, they want you to go the long way on these. So if they say use a system of equations for something that has no system, call the two sides separately y's and then go graph it and see where they cross. So get your graphing calculators out. Let's graph these and let's use our good old second calc stuff, intersect features and see where it crosses. Where do these two things cross? I don't know. That can't be right. I'm not sure. Graph them both separately. In my mind, I'm thinking these two coordinates are where they cross, but I very well could be wrong. It's a lot to do in your mind really quickly. Agreed? Getting some agreements? Sweet. So that's how you would do it if they gave you something like this. But only if they say, solve this with a system of equations. Me, I would not do that. How did I do it in my mind? I just moved everything over and set equal to 0. And it did factor. So I knew my two x's were 5 and 1. But if they ask you to do that, go do it. They say solve it with the system of equations, and there is no system. Make the two sides equal to y. Go graph it, and then see where they intersect. So that's kind of dumb, but if they ask you to do it, that's how you do it. All right, that's about all there kind of is to this stuff. Now they get some more funky things in here, but really it's not any more complicated. Let's just pick another problem or two, and then we'll call it a day. How about this one? It looks interesting. It's got fractions. Fractions are scary. So x equals 1/18 y squared. That's crazy. And secondly, they're telling me what y squared is. It's negative 18x plus 72. So just dive right in. It's a system of equations. You can use substitution or elimination. I would just take the thought out of things most of the time and use substitution myself, because number one's already got x solved for, right? Here's what x is. X is this stuff. So we're going to plug that into equation 2, and we'll see what it turns into when we do that. Could have done elimination. I see x's in both equations. I see y squareds in both equations. Lots of ways to do it. So if you were going to do something different, don't beat yourself up. It probably was fine too. Okay, equation 2 now reads y squared equals negative 18. And there's the x. From equation 1, x is 1/18 y squared. Oh, I see a plus or minus 6 coming down the road. Let's see how. So you substitute it in from equation 1. This is what x is. You plug it in. Now we're down to one equation with one variable, just like any other substitution would be. It's just all y's now. Let's clean it up, though. Now, actually, this is not as scary as it looks over here, because you have an 18, but you have a divide by 18. So what do? They just go away. I got an 18 and a divide by 18. That's going to be nothing. But I still have a negative, and I still have a y squared. So we got out of fraction land pretty darn quick on that, which is sweet. Thoughts on what to do now? Yeah, well, add this over. If you got a y squared and you add another one over, that'd be 2 y squareds, correct? I agree with that logic. And we're trying to get the y's by itself. There's a 2 in front. We can get rid of the 2. We can just divide everybody by 2. Why not? Let's divide both sides by 2. So now I know y squared equals 36. Best way to solve this really quickly is this, if you got the variable squared all by itself, just take a square root. Don't forget your plus or minus, and the square root of 36 is 6. So there's 2 possible y's for this. Positive 6 and negative 6. No matter which one you plug back into this equation and you square it, positive or negative, if you square it, it's going to be positive, right? So if you plug that one in, 6 squared is 36. Anybody know what an 18th of 36 is? Or 36 divided by 18? It's 2. So in either case, you get x equals 2. So x is 2, and I'm going to write this twice because that's what I got. I got 2 answers. So I'm going to say x was 2 when y was 6. Or we also figured out x was 2 when y equals negative 6. So 2 solutions to that. And again, consistent and independent stuff right there. And there's really not much else to this stuff. We won't do it, but one more time just to harp on the point. If they said, use a system of equations to solve this, I don't see no system. What do? You call one side y, right? There's one equation, right? Call the other side y. There's your other equation, correct? And then you just go graph them, right? And see where they cross. So if they ask you to do that, make sure you set up that way. Otherwise, just do what you always do, elimination, substitution. You might get out multiple answers this time because these are curvy things that might cross in multiple spots. Nonetheless, the procedure for substitution elimination is identical to what you used to do. Any questions over anything, guys? Pretty straightforward, I thought, today. Not a hard lesson. So there you go. You got homework 3.7 due. Homework 3.8 is brand new, due Monday after the break. Again, shoot for getting that done. You got work time today. You'll have work time tomorrow also. No reason you can't get that done and walk out of here with nothing to worry about but eating. That concludes today.